Continuing on, if I look at the next problem up, again, I need to sketch the region. That's mainly the main idea. So here, it's more plural than anything. And if I'm looking at this, trying to figure out what they're talking about, this says, let y run from radical 3 to 3. Radical 3, 1.7 about. I'm going to shift this down a bit. Okay, we can fix that. Let's do it all over. Here we are. You know what? Let's do the graph on the left and the interval on the right. Okay, so if I run from radical 3 to 3, and I notice that x runs from y, x equal y, I'm sorry, x equal positive, so x equal the square root of 9 minus y squared, a circle with a diameter of 3. Is my scale this much off? That doesn't look like a circle. Oh, I'm sorry. Take that back. Okay, no wonder. Okay. Circle with this 3. No wonder. I'm like, wait a minute. Why does it look so deformed? So it should look something like this, right? It runs from that to x equal y. X equal y is a line cutting at 45 degrees. So what are they talking about? They're talking about this region. An odd region. Okay, no problem. Well, let's see. We could fix that. That is r d theta. No big deal. And theta runs from, if you really pay attention, theta runs from pi over 4 to pi over 2. And r runs r runs from the circle with a radius of 3, that's simply 3, right? And where does it terminate? It terminates at the line y equal 3. That is r sine of theta equal 3. So 3 over sine is 3, the cosecant of theta. And since that's a radical 3, if you put it in there, you will get 3. That'll match. Perfect. Okay. Then what? Evaluate the integral by transforming it into equivalent polar. I have a few examples. A, you want to figure out the double integral. Y is r the sine of theta, before you forget, r cosine of theta. dA is r dr d theta. And how does that work? What's the region? So the problem is really trig. Can you sketch the graph of that? The calculus is simple once you get that. R is the region in the second quadrant enclosed by the circle. Let's say this is 3. Enclosed by this circle. The line x equals 0. And y equal negative x. Y equal negative x. So what are they talking about? They're talking about in the second quadrant. They're talking about this region. Do you agree that theta runs from pi over 2? to 3 pi over 4. And r runs from 0 to 3. There it is. Nothing to it. Fairly simple. You could say that is r squared times the sine of theta minus cosine of theta dr d theta. Integrate with respect to r first, that's a constant, and proceed. That's fairly simple. Any problem that you see in here that you're having a hard time integrating, ask me in class, our class session, and I'll be more than happy to show you how that works. How about this problem? If I really want to do this, again, I need the graph that's half of the problem, more than half actually. This is going to be the double integral of 1 over 1 plus r squared r dr d theta. Well, that's pretty good, because if you let u equal this, du will be 2r dr. The integral is fairly simple. And how does it work? I have a circle with a radius of 3 again. Better. Okay, and I'm looking at, what is that? That's x squared. That is r squared equals 3r the sine of theta, or r equals 3 the sine of theta. I know that's a circle with a diameter of 3 wrapped around the positive y-axis. You know what? I'm going to really blow this back up. I don't want to scale it small. I want to scale it regularly, so I can see this better. There, a circle. What's going on? With a radius of 3. 1, 2, 3, 1, 2, 3. Here we go. Oh, missed it. That's a circle with a radius of 3. And now I have a circle centered around the positive y-axis with a diameter of 3. There it is. What are they talking about? They're saying the region in the first quadrant, we're only worried about the first, enclosed between those circles. Enclosed between those circles. What does that mean? That's the area between them. It didn't say inside of both. It says between the two circles. So how do you do that? Well, that's fairly simple as far as polar. I keep on saying simple. It is to me, really. That runs from 0 to pi over 2. Quadrant 1, yes. And r runs from what? Do you see that r runs always from the purple curve? The purple curve is actually 3 the sine of theta, and it terminates on the green, and the green is r equal 3. And the integration of that is going to require a u sub. We know how to do that. Luckily, we know a lot of math, right? And how about this problem? How are we going to do that? Well, the same deal. This is going to be the double integral. Let me leave some space. Here we go. Of 1 over 1 plus r squared r dr d theta. So the integration is really simple. I need the region. R equal 1 plus the cosine of theta. Right? I know what these graphs look like. At 0, I am at 2. At pi over 2, I am at 1. At pi, I am at 0. Those graphs look like this. And I know what this graph looks like. At 0, I am at 1. At pi, I am at 2. Pi over 2, I am at 2. At pi, I am at 3. 3 pi over 2, I am back at 2. And at 2 pi, I am at 1. So how does that work? What do they want? Inside, it says inside of the purple, outside of the green. So they're talking about this region. And how does that work? Well, if I start r equal 0 and I run to this angle, I don't know what that angle is, I'll get it in a minute. That's theta. R will run, it seems, all over this region. It runs from the green is 2 minus the cosine of theta, to the purple. The purple is 1 plus the cosine of theta. And how am I going to find that angle theta? I'm going to figure out where those intersect. Where was 1 plus the cosine of theta equal 2 minus the cosine of theta? That's when 2 cosine of theta equals 1, or cosine of theta equals 1/2. I have a reference angle of pi over 3. So I got this to be pi over 3. And I could multiply this by 2 to compensate for the bottom, or I could run from negative pi over 3 to pi over 3 if I want. It really makes no difference. The same as what you did your last semester when you tackled this section.